Okay, so today I'm going to be the second part of this architectures tutorial that Fred started in the first half. So I've given it kind of a subtitle of Quantum Architectures, Space-Time Trade-offs in Mixed-Radix Quantum Computing. And so today I'm going to talk about a series of work centered around the use of multi-valued logic as an example of Fred's breaking abstractions, where in most classical and quantum systems, we're used to working with binary objects. But today, we're going to challenge that position and think about systems which may be especially space-limited, for example, the number of physical objects that you have available, and ways we can squeeze more out of machines available to us, and in some cases, obtain unexpected wins in terms of expected error or speed of execution. And in particular, we're going to look at the story which began with high-level circuit constructions that Fred alluded to earlier in 2019 at QIP, these decompositions of complex instructions, and how they evolved into a systems-level study of mixed radix and temporary use of high radix quantum computation. So current quantum hardware typically supports operations between at most 2 quantum bits at a time, and a key step in this compilation of input programs is to break down these large blocks into smaller executable pieces. Current devices are also noisy, meaning we want to minimize the total number of operations and runtime. And finding decompositions of large circuits, which are both low in gate count and low in depth, are especially important. And finally, current quantum computers have a limited number of physical devices, or qubits. Many available decompositions make use of ancilla qubits, which begin in a known zero state. And the more ancilla decomposition requires, the smaller the total size of your maximum computation on that hardware can be, because you have to reserve so much space to be used as ancilla for the decomposition. The best decomposition is going to be one that balances all of these trade-offs. For the first part, we'll focus on circuit-level optimization to reduce the total number of ancilla we need, which will be usually none, while still using a small number of gates and having a low depth. So let's look at a really quick example, and we'll revisit later. And this is just a 2-control Toffoli gate, and it has the typical decomposition on the left, where you use these 6 C-naughts and a bunch of single qubit gates. And on the right, we have, if we allow ourselves access to additional states, say the 3rd or 4th level, we can actually change that decomposition into one that uses only 3 2-qubit gates and obtains the same kind of overall goal of doing the AND. And at face value, this looks kind of limited, where all we've done is save about 3 2-qubit gates. And that's true for these small cases, but as we kind of extend to the generalized case, we get even more value. Okay, so let's just give a quick review of the basic objects of interest. So today we're focusing on the generalized qubit, or the Qudit. Just like classically we think about a multi-valued system where each object can exist as one of d possible values. We have the same generalization for quantum systems, where a Qudit exists as a superposition of d energy states. In many physical systems, we can make use of these additional states to implement some gates. Today we want to think about using these additional states actually as logical states, not as these kind of like temporary fleeting values. Qubit operators have fairly natural extensions for qubits, for Qudits, and for the most part, we don't need to think about all possible of these operators, and instead can think about some generalized examples. So for example, we have this xij, or the flip between the coefficients of the ith state and the jth state, and these kind of increment operator, this x plus k, which just shifts all the coefficients by k mod the dimension d. For the circuit decompositions today, it's sufficient to think about just these classical permutation operators, but of course we could extend them to say H gates, RZ gates, RX gates, etc., on either the whole space or some subspace contained. We also care about the corresponding 2-qubit operators, and again, here we only need to think about the controlled versions of the gates we just saw. The one controlled X gate or C0 gate that we're all used to on the left has its corresponding generalized form as C controlled and these kind of permutation operators. We could replace that with something else if we wanted, but for our cases, we only need to think about these permutations, x plus k and xij. And the C can be any value from 0 to d minus 1 for whatever the control you want to do. Certainly, we could be more expressive by allowing any 2-qubit operator, but current machines don't often support an overly specified gate set. Even this one that we've labeled here is a little bit overspecified. We can be complete without having all of the possible C's and X plus J's, etc. And so, but it's realistic to define some smaller set that you could possibly calibrate or efficiently calibrate. Okay, so the first type first part of this, we're interested in this temporary logical use of higher energy states. And so to get a flavor of how this works, we can use temporarily and apply it to the Toffoli gate. So this is the same thing we just saw before. We're familiar with this decomposition of the Toffoli gate into its textbook decomposition. An important observation, though, is to note that all inputs begin binary. Throughout the entire computation, they stay binary, and at the end, they're output as binary. In contrast to this other decomposition that I showed before, we can consider this alternative approach where we temporarily allow access to a third state or temporarily we're ternary. And so how does this actually work? So the inputs are still binary and the outputs are still binary. However, we place no restriction on which states the inputs can take during the computation. I mean, of course, we're bounding it by 3, but we could allow even more, as we'll see later. So the first gate, this one controlled x plus 1, is going to change the state of Q1 to be in 2, if and only if both Q0 and Q1 are in 2, effectively recording the AND on top of Q1, which then allows us to control the desired X gate on the target if they're both in 1, which is exactly what the Toffoli gate is doing. And the end is to uncompute, so we can return back to binary. And so we've effectively done the same decomposition using a smaller number of gates. Okay, so let's look at the generalized form. So the goal is to apply some desired unitary, could be the X gate like before. And we want to do that if and only if all of the controls are in the 1 state. And so for prior work, without the use of ancilla, so without these additional 0 states, the best known decomposition of the gate is linear in depth, with a very large and practical constant in front of it. To obtain a logarithmic depth decomposition, we'd require the use of a linear number of ancilla, or these clean known 0 states. And in the original decomposition, we can store groups of ands into these ancilla and then recurse on this in sort of a binary tree sort of way. So you can kind of use that binary tree to reason about the logarithmic depth of this decomposition. It's fairly straightforward. Instead of thinking about just kind of 2 gates collecting pairwise, we can do this in triples and then decompose later. So we're putting on Q1 the AND of Q0, Q1, and Q2. So the whole triple is recorded on top of Q1, and then we can recurse. And at the end, we're applying the final target unitary to the target if they were all in the 1 state. So the benefit that we're getting from this, well, actually, sorry, I should say, in this decomposition, there's no additional ancilla. There's no extra space that's allocated. These are all the controls in the decomposition. We need no additional space to record these temporary values. We instead record it in this additional state that's local to the computation. And so the benefit afforded by extra space can actually be realized by using this extra space that's local to decomposition. So if we think about kind of expanding vertically instead of horizontally, where horizontally meaning we add additional physical devices to our system, the alternative is to add additional states that are accessible in our computation. This still has the same kind of value as before, where it began as binary and it ended as binary in its own computation, meaning we can kind of stick this circuit anywhere that the original generalized Toffoli appeared. So in hardware which is extremely space limited, for example, all of today's available machines, ancilla severely limits the total maximum size of computation which can be performed because we have to reserve that space to perform the decomposition. So for comparison, we can compare circuit depths and gate counts to corresponding qubit only and qubit only plus 1 ancilla, so you have a little bit of extra space. And using the same number of physical devices, we can obtain low gate counts and asymptotically lower depth decompositions for example circuits like this. So you can see here on the right, I'm showing these 3 different decompositions. They all have the same kind of asymptotics in terms of gate count with a better scaling for the Qtrit version. And the same for the depth, where we actually recover the logarithmic depth from the best known using ancilla decomposition. At the circuit level, this looks like an obvious win. However, error in Qudit systems is expected to scale with the dimension of the devices, something like quadratic increase in the total number of coherent error channels and a linear reduction in the coherence time of additional states. So for example, you can think about the T1 time of the 2 state being about 1/3 of the T1 time of the qubit, or some other kind of close value to that. So overuse of these states or full translation into Qudit systems will certainly not win, since we know that translation to binary to ternary gives it most constant gate or depth advantage. However, because we can produce decompositions which temporarily access these states and which use so many fewer gates and lower depth, we can still maybe extract some wins. In simulation, this is the case. So compared to its qubit-only counterparts, the decomposition, even with increased error rates for the qubits, results in higher fidelity outcomes. And so, Fred noted before, this work came out in 2019, and about 2 years later, IBM published an implementation of that smallest 2-controlled version, which you see in the bottom right here of this figure. And they showed that it worked, and the 2 has comparable fidelity to the qubit-only decomposition. So there may be some, realistic way forward to put this onto hardware. Okay, so while fairly specialized and hand optimized, we had to look at the specific circuit and figure out how to make use of these extra states. This component has some real use in, for example, arithmetics. And from a compiler standpoint, we can just find and replace in application circuits with this new decomposition and never require a change in ancilla or space allocation, since our decompositions remove the need for ancilla, extending the max size of possible applications on near-term hardware. Okay, so here on the top, there's just an example of an incrementer circuit. The idea is you just add 1 to this bit. It's not super useful, but there are a bunch of Toffleys in it. So we can kind of, instead of using ancilla to do these decompositions, we can get a nice log cubed depth of this entire circuit by using this new temporary version. And then on the bottom, it doesn't have generalized Toffley, but if I want to do an adder and I want to kind of compile these decompositions into already known circuits, we can do a find and replace on even the 2 Toffley and put in our simplified kind of 3-gate decomposition and get some advantage. Okay, so this decomposition is what started down this path of using qubits. And how do we practically use these additional logical states? But the question still was, do we need to always hand optimize to obtain any wins? And what we realized about these decompositions was we wanted space in the form of ancilla, but it wasn't obvious how we can actually transfer the space we needed from the ancilla into the kind of local to the computation. So we thought, well, rather than being somewhat clever to make use of these higher states, we can actually just generate the ancilla local to the computation by compressing the information of unused qubits elsewhere in the circuit and put them into a smaller number of qubits, leaving known 0 states behind that can be moved across the machine, used in other decompositions, et cetera. And so we've called this Qubit-Qudit compression. So the information is starting as all qubits, we store it in a small number of qubits, and then some number of extra ancilla are produced at the end. So why might we want this? So when compiling quantum algorithms, some may request the use of these ancilla in order to be done efficiently. The compiler has to decide which ancilla and from where to get them to allocate. And if there are very few available, they may need to be shuttled back and forth across the machine to be used. And we also have the caveat that we don't really want to mess with the information that's stored in the qubits, but we can recover them so long as we know which kind of pairs go together. So in this circuit, I put 3 A, B, and C into 2 A prime, B prime. I just need to remember that A prime and B prime go together so I can kind of unencode the information later back onto an ancilla to obtain A, B, and C back. Okay, so the key idea here is that in a constant number of gates, I can produce 1 ancilla out. And to kind of verify this, we can look at the truth table for this. This is all just a reversible circuit. We can look at the corresponding truth table and see that C prime is in all 0, regardless of the input of A, B, and C. Okay, we can also do this for other radix. We don't have to just use 3 states. So we could also do compression into Q-quartz. And it's easier to reason about at first glance. There's 2 basis vectors with a 1 in that second position. By performing this first controlled 2-gate and then 3-gate, and then there are 2 controlled and 3 controlled flips, we can eliminate that 1 in that column to kind of obtain B prime of being all 0s. So all the information of A and B is now stored in 1 physical device, A prime. So why might we want to use one over the other? So we kind of alluded to this before, but use of these higher states usually means there's more possibility for error. And the higher we go up, the more types of errors we expect to happen. So the answer really is going to be, it's going to depend on the hardware. In practice, there's a wide variety of potential compression circuits that we could cook up. We don't even need to start in binary. We could start in ternary and go to 5 states or something. And all those circuits exist, but the kind of compression efficiency of how many kind of inputs you need and how many ancilla you're going to get out is going to depend on that choice. Most obviously, these powers of 2 is going to be nice ways to store lots of qubits of information in small numbers of physical devices, and it'll be kind of a perfect ratio. Okay, so let's look at how this compression can be used. So The idea is going to be to dynamically generate these ancilla like we thought about before instead of trying to be clever. And so here our goal is going to be an adder of two states, A and B, and then compute the sum, this S on top of B. So we will replace B with the sum of A and B, and then all the ancilla that we take in on the left, you can see them labeled, will be returned to 0 at the end of the computation. And so the question is going to be, well, how does compression help us? We already have this kind of nice circuit. It's logarithmic in depth. Our goal is going to be to eliminate all of the ancilla. We don't want to have any additional space. We'll only have A and B. Okay, so let's look at a really large circuit. I've taken only the most portion of it. And again, the goal is going to be to compute A plus B, but now we're going to have 0 ancilla available to us. We could just decide to use a different circuit. So for example, a linear depth Kakarow adder, the ripple carry adder I showed before, is linear depth. It's okay. It used no ancilla, but it's not particularly efficient. And instead, we can reobtain that logarithmic depth decomposition by doing this dynamic generation of ancilla. Okay, so the strategy is fairly simple. Break all the bits into a constant number of blocks, and that number will be determined by the radix of the compression, whether you're going from 2 to 3 or 2 to 4, etc. And we also want to note that adding low-order bits in addition and high-order bits in addition can be kind of done almost independently, so long as you know the carry of the lower-order bits. And so how do we do it? All the blocks except the first get compressed to produce the necessary number of ancilla for that one block. So this topmost block where I'm computing A plus B on a subset, and everything else gets compressed. That will be guaranteed to have enough ancilla to do this A plus B2 in logarithmic depth with no additional space because we've generated that space local to the computation. And then for every subsequent block, we can compress what we've just finished. We already did some addition on A and B. We can compress that since we're done, record its carryout bit first, I suppose, and then uncompress the next block that we need to do. And because all these blocks are kind of the same size, there'll always be enough ancilla to do it, and we can always get the best case decomposition. And at the end, there's some cleanup that we have to do to fix all the carries that we've stored, but it's also not a problem. Okay, so from a circuit decomposition point of view, clearly there's a benefit. We've reduced the gate counts, we've reduced the space requirements, but this isn't the whole story, and the remainder of today's discussion is going to be centered around these more practical questions about, is it realistic to care about higher and mixed radix quantum architectures? So we'll go back to the Toffoli decompositions, I think maybe the last time, maybe the one more time. And on the left, we saw before using at most intermediate Q-trits, and on the right, we can see you can kind of change the circuit just a little bit to use intermediate Q-quarts. So instead of storing things up to 3 levels, we're now going to allow ourselves to store up to 4 levels. And this simplifies it a little bit. We don't longer need these 3 or these 2 controlled gates. We can use only 1 controlled gates to get the same effect. And then if you keep increasing beyond 4, there's not really any obvious benefit. So these are kind of examples of that. And so on their own, the evaluation is fine, but ignores kind of the spatial locality and the relative cost to move the information across the device. So higher dimensional objects are more expensive to move, even at the circuit level. So let's take a look at that. So actually, to just do a quick aside, I think Fred talked a little bit about it, about this mapping and routing problem. So each of the qubits in the circuit gets assigned to one position on a limited connectivity hardware. So here in the top right, we're looking at this grid of this graph representing some hardware connectivity, where qubits can only interact if they're adjacent. And so most circuits cannot be mapped perfectly onto the target hardware, meaning some interacting program qubits will be placed in some distant positions and will need to be moved in order to interact. Here we might have a mapping algorithm that, say, puts this middle qubit on the top left and some other qubit in the bottom middle. And because they need to interact at some point in the circuit, we'll have to move them close together. So in our expanded gate set, QDIT movement is going to require quadratically more gates as the total dimension of the pair increases. So typical swaps like the one at the top use 3 gates, 3 C-naughts. These Q-trit, so between 2 3-dimensional objects, takes 9 gates, and between 4 and 4, 2 Q-quarts, it's 18 gates. And essentially we can think about this as swapping every 2-dimensional subspace that's available. And of course, if we had a more expressive gate set, we could probably simplify this, but I think the picture is most clear in this kind of gate set, where it's going to cost us a lot of gates to move increasingly more complex information across the device. So even though we may be saving by increasing information locality by doing some amount of compression, we now have to pay some additional cost to move information-dense objects across the device. So it's not obvious that we're still going to recover a win after we do this. So we can get a sense for this if we compile these Toffoli circuits with different allowed max dimension. In all cases, pre-compilation, we have this nice logarithmic depth, but post-compilation to grid architectures, the scaling is lost to the costly communication patterns needed to execute the circuit. In this specialized case, we still win in total circuit depth with a widening gap in the end, so on the far right, as we get to say 60 or 70 controls. And this is kind of mitigated by the fact that we can preferentially choose to move only low dimension objects, say the ones that are only ever qubits, and not choose things that are, say, the Q-trits or Q-quarts. And these circuits have relatively low use of the high dimension. We're only using them to collect some number of ands throughout. But in general, this isn't the case. We could think about, say, fully encoding a binary program into one that's, say, ternary. This will no longer have this kind of benefit of being able to choose which things to move and which things, and how many of them are actually in high dimension. So in general, it's not going to be the case that we can recover this win. Okay, so let's shift a little bit to the discussion of more recent work, which is aimed to evaluate the use of these mixed-radix architectures, and in general, a system which uses some combinations of qubits and Q-quarts, so 2 and 4 level systems, where we just opted to use Q-quarts because it's a much more natural view of a Q-quart as just 2 qubits which occupy the same physical location, instead of having to really reason about what is really a Q-trit, how much information is there. And so translation into mixtures of non-powers of 2 is not going to be easy. And in this view, we can think about our standard gateset just embedded in some higher dimension. So when we think about 2 qubits in the same location, so here there's just a qubit on the far left. A Q-quart could be viewed in the kind of this expanded form as 2 qubits worth of information, Q0 and Q1, and then again another Q-quart on the far right. And so, at face value, it seems like nothing changes except the relative locality of the information. So more densely packing the limited connectivity hardware. We can kind of virtually expand that connectivity because now 2 Q-quarts are adjacent, which is really like 2 pairs of qubits that are fully connected. So each of these lines indicates necessary gates in our expanded mixed-radix architecture, and these are the times it takes to execute those various implementations. And we can see these values vary widely on the location of the information. So the times for these gates are kind of necessary. So before we were just looking at gates. We said, how many gates does it take to do a decomposition? How deep will that circuit be? But in reality, we don't want to think just about the gate. We want to think about how long does that gate actually take to implement on hardware. Because if we just look at gates, we might say, oh, this is 1 Q-quart gate and 1 qubit gate. Are those really the same? Or is that a fair comparison? So instead, we want to kind of break that and think about how long does it realistically take to execute. So, and when we started this, we found that theoretically, we're expecting that the durations of these gates in terms of pulses are supposedly going to scale quadratically with the dimension of the system, so similar to how these swaps scaled. But what we're interested in is maybe in this kind of low dimension regime, qubits, Q-trits, Q-quarts, that they're actually scaling kind of weakly quadratically and we can recover even more advantage. Okay, so to do this, we turn to the pulse level control to realize these gates on some example hardware. We could do the same thing for some other system as well. The state of the quantum system can be purposely manipulated by applying some external control fields that are tuned to whatever that particular hardware is. So for example, we could think here about applying microwave pulses to superconducting qubits. The evolution of the state of these objects is determined by some corresponding time-dependent Hamiltonian, this h of t. And we can write this as the drift Hamiltonian, which we cannot control, and the control Hamiltonian, this hc of t, which we can control by modifying the strength of 2 control fields, in this case, p and q. The goal is going to be to find p and q in order to realize some target unitary, and that can be done by repeatedly solving the Schrodinger equation and then adjusting p and q incrementally until you obtain some realization of the target. So here we have these targets from before. All these gates are our targets. We want to use this system to find these gate times that they correspond to. There's lots of systems out there that can do this. For example, Grape or Jukebox are systems that you can use. You can plug in the target unitary, you can plug in this Hamiltonian, and then you can just ask it to solve what should P and Q be. And these systems typically require you to specify the total amount of time that the pulse can take and the maximum amplitude of each of P and Q, which bounds the minimal time T needed to realize the target with some given fidelity, usually say 2 nines or 3 nines of fidelity. In this work, we were considering a much larger Hamiltonian. So instead of thinking about just qubits, we now want to think about Q-trits or Q-quarts, adding additional states, which does increase the complexity of solving this problem and making it much harder to do. I think in the worst case, it took us up to a day to find kind of an optimal solution for our worst case. Okay, so let's look at an example that realizes a Q-quart Hadamard gate. The objective being that when you start with any pure logical state, you end in some uniform superposition of each of those states. And rather than examining the actual pulses themselves, we can look at how individual populations evolve over the course of that pulse. Here we can see that after using one of these optimization frameworks, we get population evolutions that look good. So for example, at the top left, we start all in the 0 state, and after the pulse finishes on the far right, we're now in an equal population of 0, 1, 2, and 3. I should also note there's these additional states, these 4 and 5, which don't have any population at the end, which is good, because as we increase the number of levels that we're considering, we become especially more prone to what's called leakage, where we might leave population in states that we don't want to manipulate, which aren't logical states in our system. And so in doing the optimization, you can add these additional levels into the optimization and make sure that they never obtain population, or at least they end in a 0 population. So in this work, though, we weren't interested just in finding good pulses. So the objective might usually be just find one that gives me high fidelity outcome. We also want to realize these gates with the lowest possible duration, up to some, without losing too much in terms of error. And so we want to make sure that we're both fast and high quality. Okay, so before you start, it's not immediately clear what's the minimum amount of time that you should be given for any particular operation. And it's going to be operation dependent. And rather than linearly or binary searching over a wide range of possible times, each starting from some new random guess, we can employ a technique called incremental pulse reseeding. So in this strategy, you start from some optimized pulse for some guessed time. It might be wrong. It could be good or bad, or below this kind of desired threshold of quality. If it's not, we can extend the duration of the pulse and pad that pulse with some do-nothing operation and use that as the new starting point for future optimizations. If it is below the threshold, i.e. it was good enough, we could also trim that pulse and use that as an initial guess. And we can continue this process of using old pulses to seed and continue searching for minimal duration versions of the desired operations. Okay, so in this figure, we're kind of explaining, we started with this 70 duration pulse. It failed to meet the criteria of how good it should be, so we padded it to 78 duration. So we extended the pulse duration, but used the same optimized pulse from before as kind of a seed to start to guide the search, since it's a heuristic program. And then re-optimize that to obtain some new pulse and keep doing this until we obtain some low duration pulse that satisfies our quality requirement. Okay, so finding optimal pulses is certainly hard, and guaranteeing that they're minimal in duration is also hard for practical reasons. So for example, we only have a limited amount of time to calibrate, say, our realistic system in order to maximize the uptime on an industrial system. And we have to rely on these types of heuristics like grape or jukebox or something. And so a naive alternative to this reseeding technique might be we'll just sample a bunch of random starting guesses and then choose the best. As expected, though, not all initial guesses converge to the same outcome. So in each of these plots, there's 20 initial guesses. They occupy a range of different fidelities post-optimization. They're not all converging to the same thing. And also as expected, as the maximum allotted time decreases, so we go to the left on the axis, we're less likely to obtain a high quality outcome because there's not enough the duration to perform all the transformations that we want. So in this example, for an X gate on an 8-dimensional system, we don't even obtain what the IPR, this reseeding scheme, obtains by using good starting points. So with this technique, though, we were better able to study the empirical and practical scaling of different operations on realistic hardware as the dimension of the qubit increases to better understand what constitutes the practical usable range of these high-dimensional objects. As we can see for up to dimension 8 on the x-axis, we have a weakly quadratic scaling pulse duration, This hints at the fact that as we move beyond thinking about just gate level optimizations or decompositions, it's not as bad as it could be. Certainly it does scale quadratically. It's better fit by a quadratic curve than a linear one. But in this low range of say 2, 3, 4, it does scale nearly linearly, meaning that we're not kind of exploding in pulse duration as we increase the dimension. So we're not completely out of luck by adding a couple extra states to our system. And so using this process of this reseeding technique, we can obtain all those pulses that we had before from that table. Okay, so with these gates in hand, we can go back and think about how can we execute programs utilizing this some amount of qubit and Q-port compression, either dynamically or otherwise, just pre-assigning two things to the same location. And maybe instead of calling it compression, we could call it co-location. We have individual physical devices, and we want to store multiple qubits worth of information in those individual spaces. In this adjusted picture, we get a sense for these inherent trade-offs, so dictated by how expensive gates are between respective objects. So some gates on encoded information were fast. So for example, internal to the Q-port in this middle, you can see that they're labeled as fast. These C-naughts between the encoded information are really quick. Their pulses are very short. But we might pay a cost by having more expensive gates between Q-ports and qubits, or even between two pairs of Q-ports. And even in kind of the best case scenario in terms of space, where we've halved the total physical devices that we need to execute our program, we'll mostly be using these medium-slow operations. So there's definitely a trade-off between how many things should be compressed into a smaller number of objects. Okay, so one thing that might not be immediately evident, though, is that while the expected duration of the gates on high-dimensional objects gets worse, some gates are actually faster because they become equivalent to single qubit gates, which are usually much faster than interacting two distinct physical objects. So for intuition, we can think about encoding two qubits as a Q-port, and since we still want to think about them as distinct qubits, we can think about how their corresponding individual operations look in this encoded system. So in this kind of simplified picture, we've taken two qubits of information, we put them into a single device, and we have this new vector representing all those coefficients. And we can see that what needs to be transformed to perform certain operations kind of changes in this new model. So an X gate now needs to transform two pairs of coefficients in order to accomplish an X on a subspace. But a C-naught, however, instead of having to interact between two objects, needs to change just one pair of coefficients internal to the Q-port. And so you can see how that reflects in the actual gate time. So we've highlighted a few. So the blue gates in the bottom are the X gates on different pairs or on individuals. And you can see they have different durations, 66 nanoseconds versus 80 to 90 nanoseconds. And then similarly for different C-naughts, they actually have dramatically different durations. So if I perform a C-naught between two pairs of qubits, individual physical devices, it could take something like 251 nanoseconds. Whereas if I do a C-naught internal to the computation, it takes only, say, something close to an X gate, 80 to 90 nanoseconds. So then we should ask, well, which qubits should be compiled or mapped into the same locations? So intuitively, there's some obvious answers. Qubits which interact frequently should be co-located to maximize their use of this shorter, quote, internal C-naught gate. However, what turns out to be more impactful is using this compression to modify the structure of the program's interaction graph. So every program that we're thinking about has some corresponding interaction graph. So for example here, this generalized Toffoli has its corresponding graph next to it. And then this adder that we saw before in block form now has its also corresponding graph. And because we know there aren't perfect mappings from these program graphs onto the hardware, we know that we will need to add some amount of swap operations. But if we consider these two simple programs, naively, they have two triangles in them, or some number of triangles in them. And when mapped to the grid, this will need some swaps. However, I can kind of think about combining pairs in this graph to change the structure. So for example, on the far left, we could map 0 and 1 onto the same location, and that triangle disappears. And now I only have some linear connectivity requirement to accomplish the same triangle structure. And I could do this again for, say, 3 and 6, or I guess that's 5 and 6, and 3 and 4, and then the whole graph actually becomes linear and very easy to map onto the target hardware, eliminating the need for swaps, while maybe getting some additional benefit from the internal C-naughts that we've found. For general program graphs, though, this isn't obvious. So on the right, we can see for sample programs of all possible choices of co-mapping. So we think about every possible pair that could be mapped into the same location and how that impacts a metric we call expected probability of success, which roughly bounds how good the program could be if we just say multiply all the gate errors together. So many choices actually lead to a decrease in this metric, so getting worse. And even those that are locally best won't be necessarily used in the best pairing in the end. And notably, not every compression is good. Just by pushing things together does not necessarily produce a better circuit execution. And in order to find that kind of optimal structure, we would have to look over all possible subsets of mappings, which will be ultimately hard. So instead, we need to think about some heuristics that we can use. So across kind of a range of benchmarks, we can study the effects of choosing different pairings according to different strategies and compared to this ideal scenario where we looked over all possible subsets. And here over a range of sizes, we can study the ratio of expected success if we use Q-quarts versus if we use the expected success if we use a qubit-only system. So this ratio here on the y-axis is if you're better than 1, that means doing some amount of compression was better. So co-locating some number of qubits was better. And if you're below 1, then it was always a loss. So for most programs, just forcing every qubit to be encoded, so this FQ or full Q-quart baseline, so you make everything, this is the best case for the space. Everything is co-located, you've halved the total space requirement. It's almost never a win. However, if you're more selective about which pairs that you co-locate, you can actually recover some amount of advantage. Gates, of course, aren't everything, and part of the motivating factor was to consider the duration of pulses, and if we consider the expected probability of decoherence, we can see that this is sort of as expected. We're never better than using only qubits, so we're always less than 1 in this ratio. And so while specialized compilation methods can mitigate this loss, so this gap between the orange line and any of the other selective methods, it's still poorly scaling in all cases. So this isn't particularly motivating, but there are two factors that mitigate this fact. So one, we're always going to be space saving. So any compression results in larger possible computations on your hardware. And if the result is non-trivial with some error, that's probably still a win. If you can still distinguish the correct answer, then it might be okay. And two, in combination with the previous data, so the gate product, we might still get a win when we take the product of those two values. So why is this the case? Wasn't the point of the circuit durations to get better? So yes, but we're considering worst case decoherence times for higher dimensional states. So if they kind of remain on the poor end, so this kind of linear scaling or loss in the coherence times, then we probably won't ever get the circuit short enough to get a win. But if we can do some amount of optimization on the T1 times for these high dimensional states, we could kind of recover a win. And if we consider something that's not just a bound where we're taking the product of gates or coherence or decoherence, something closer to a full simulation of the system, we'll actually see that gets a lot better. So as computer architects, Fred alluded to this kind of design space exploration. And so we make a lot of choices, many of which are based on the current state of quantum machines. And they aren't necessarily indicative of long-term performance of the proposed technologies like qudits. And so it's often advantageous to think about how applicable are these techniques going to be as the parameters change. So currently Qtrit and Q-quart decoherence times are much worse than the coherence times of qubits, some of which is because of physical limits, and some of which is because hardware developers just aren't optimizing for it. And so as an example of this kind of study, we can study what happens if the coherence time of the Q-quarts, the fourth state, improves relative to the qubit coherence time, up to this limit on the far right where the qubit T1 is equal to the Q-quart T1. And we can find crossover points for different types of programs where we kind of need to target as hardware developers in order to get a win out of this kind of mixed-radix architecture. You can see for nearly every program, this crossover point happens at some point. It's never always worse than the qubit-only counterpart. So what about more complex gates? So can we get even more benefit out of using mixed-radix? As we saw before on encoded qubits, these so-called internal CNOTs become nearly free. They're equivalent to some single Q-quart gate, not need to interact over the coupler in the system. We can go one step further and think about encoding 3 qubits in a single Q-oct, for example, an 8-level system, which can enable a very fast Toffoli gate on the encoded triple, with some cascading loss on lower dimension gates. So you can see the Toffoli gate requires just one change in the coefficients. The X gate on 1 qubit in the encoded system now takes 4 transitions, and the C not taking 2. So there's some kind of increasing effect on low dimension gates in the system, but we get a really nice fast Toffoli gate. So using Q-oct is probably a little bit outside the realistic range, to be decided, but practically speaking, we might not want to go that far up. The amount of error in the systems is going to increase very poorly, and even worse for these kind of cross-dimension gates. If I want to interact this now triple with some other double or single, those gates also get much worse. So we're definitely trading off by adding more dimension. But what about some hybrid system? So encode again qubits into Q-quarts and leave some as qubits, but maybe we can simplify these complex gates like Toffoli gates in this mixed-radix system without ruining every other gate. Okay, so I said maybe that was the last time, but one more time. So let's revisit the Toffoli one more time. On a typical grid architecture, and using the standard decomposition that we saw before, not only do we need to perform the 6 gates in the decomposition, we might also need to add some amount of swap gates, leading to an overall really expensive implementation of these complex multi-qubit gates. In fact, this one takes, with those numbers we had before, about 2,000 nanoseconds, and it's spread across 3 different physical devices. In contrast, if we think about our hybrid scheme, where some of the controls are co-located in the same physical device, we can actually implement the Toffoli gate using only 412 nanoseconds, kind of a 4x speed up, and using only 2 physical devices. Okay, so with this motivation, we can expand the total gate set with this new additional table and add in the CCX, CCZ, and the C-swap gates, which are all notably faster than decomposing in the traditional qubit-only way. What's significant here is, again, that the compression choice matters. Which qubits are controls and which qubits are targets change the duration of these gates. If they're in the encoded pair or if they're not in the encoded pair, that also changes it. And this will have kind of significant impact on the corresponding pulse. You can see these numbers kind of vary widely depending on those parameters, where the superscript indicates which triple is performed, is engaged in the gate. Okay, so let's expand on that a little bit. So when both controls or both targets in the case of the C-swap are in the encoded pair, this results in an overall faster gate. So why is this the case? If we think about how the Toffoli operates, we wanted to activate when both controls were in the 1 state. In the encoded pair, this corresponds exactly to a 3-controlled X gate. So we're just checking in the 3rd state. If there's any population there, then they're both in the 1 state, so it activates the Toffoli. And however, it actually makes more sense to simplify this choice and not think about controls and targets, and recall this kind of simple relation about our CCX gate, and we can transform them into CCZ gates, where now we're kind of target agnostic. We no longer need to think about which thing is a target, which thing is located where. We can instead just think about, is it a Toffoli or not? So one strategy we might think to employ is that if the Toffoli gates are so much faster, why don't we just dynamically compress and decompress the information? We can just map everything as qubits, use already known algorithms for this, and then when we want to do a Toffoli gate, compress the controls into the same location, perform the desired Toffoli, and then decompress back into qubits only. So it turns out that's possible. It does work in this kind of encoding and unencoding dynamic scheme. And it performs better than qubit-only cases in this case, in these several benchmarks. But it actually doesn't outperform if we just consider that expanded graph, where if we think about Q-quarts as 2 qubits and we can possibly map into the upper and lower positions, we can actually just do better than that. We won't need to dynamically change the positions. Either way, though, we can extract even more benefit out of our systems, our mixed-radix systems, but perhaps for a lot fewer applications. So we need to find applications that already have Toffoli gates in them to make use of this strategy. Okay, so again, all these results depend on particular choices in the error, the coherence time, and again, we should kind of study how much these wins depend on those particular choices. So essentially, we can view these plots here as how much better do qubits need to be relative to the Q-quartz, the high-dimensional object, before it's no longer meaningful to employ this type of technique. Again, apart from the obvious space wins, where if my provider can only give me 20 qubits, I may need to add additional levels. And so for a decent range, so up to 3.5 to 5x better, our strategy and techniques will end up resulting in a better expected quality in simulation. So that includes both coherence and gate errors. Okay, so I think we're almost near the time. I don't know if we're ending. Okay, so I guess I'll just end with a few takeaways, then we can do questions. So we are still early in the development of usable quantum computers. And so finding ways that we can expand what we can compute on whatever hardware is available to us from these cloud providers is important for near-term usability. And so high and mixed-radix systems architectures could help us expand this frontier, so increasing the total possible computation that we can perform on limited hardware. And what we've shown in this kind of sequence of work is that a full stack optimization, including direct-to-pulse gates and tailored compilation techniques, can yield wins over kind of the qubit-only architectures that we have available to us now. And I guess I also just want to say thanks to all the students that kind of took over this work after I ended. So in particular, Andrew, Lidikin, Max, and Jason, and Natalia. I think one of them is here today. But all right, that's all. I'll take some questions now.
Oh, hey, thank you for your talk on qudits. I was just curious, because I work a little bit with qudits myself, and some of the higher energy states, they're harder to probe because like when you read out, the transition's weaker. Do you have any tips on like how to get the transitions to be stronger?
Yeah, I purposely omitted measurement. It's been a sticking point. So that was kind of the motivation at the beginning. I said everything began in binary, ended in binary. And so in those cases, if we can kind of guarantee that, we don't have to worry about this measurement problem, where we just know we'll just do our same measurement as before. And that could be the case for this other kind of mixed radix thing. If we like kind of reserve an ancilla to do a decompression, we can measure those things and then continually use that additional space to read out. So it would spend us some more time, but we could always read out in qubits if we need to. But it is a problem. Reading out multiple states and distinguishing them is hard. But we can avoid the problem.
Yeah. And then I guess my second question, do you have any insight, like, is it possible to get like a metastable state, let's say like, that's a higher energy level in a transmon?
Yes, it should be able to, yeah.
Sure. Okay. Yeah, thanks.
Hi, thank you for your interesting talk. So I have just, my questions are really, I'm going to ask you to summarize some of the stuff you said on a high level. So firstly, could you go to the slides when you introduced like Qubit-Qudit Compression?
Oh, like a long time ago? Circuits?
Yeah, Qubit-Qudit, yeah. So I just wanted to ask, like, could you recap what was the role of these? Like, I sort of see them as like, yeah, a channel that's like, you start with 2 qubits and then, okay, you have a Q-quart at the end. So could you just recap, like, what was the role of these?
Yeah, so if I go, this is kind of the example I would use. So this circuit has no initial ancilla, but it wants a lot of ancilla in order to be effective. So to get a low depth circuit, I want, say, a linear number of ancilla, but I don't have them. But I can generate them if I do this compression technique. So I can just take pairs or triples and produce the zero, and then just stick this basic decomposition in with those zeros now. So these circuits are just playing the role of dynamically generating the ancilla in like during computation.
And the point here is that on the left-hand side, we have like what are physically Q-quarts, but they're only being used as qubits.
That's right, yeah.
Okay.
The levels exist, we're just not accessing them.
Okay,
yeah, that's right.
And so this is like moving all your information.
That's right.
To create ancilla. All right, thanks. And then so similar, like high-level question like this. Now, could you go back to the part on where you had like this graph with 5 vertices? So I think you called it something like Mixed-Radix.
This one?
Yeah. So so what was like the general idea here?
The idea here is that if we this is really kind of a line of three physical devices. So the far left is one physical device, the middle blue circle is another physical device, and the far right is a physical device. So if I look at a IBM machine or something, right, this is just 3 qubits or 3 dots on the machine. But in our expanded view of thinking as a Q-core has 2 qubits encoded, we can think of that as expanding this as now there's 2 qubits in each of the Q-cores, but the connectivity gets better because they're physically connected to each other. So it's like an expanded hardware graph.
Okay, got it. Yeah. Sorry, I missed that, but it's really helpful to have you explain it. Thank you. And one last thing was you were talking about like designing pulse sequences. So again, there I got a bit lost. Like, what is the role of, like, why are you having to, yeah, I guess think about pulse sequences?
Yeah, so the idea of thinking about pulse sequences is that if I think just about gates, right? So let's just go back to like the circuit, right? These are like equivalent circuits. Maybe the controls are different, but you could write the same one. So they look like they're the same. But in reality, so these plots, like for example, if I look at Q-quarts and Q-quints, so 5-level and 4-level systems, the plots are nearly identical. The depth is the same, the gates will be the same. But those gates become a lot more expensive if I think about how long does it actually take to execute on device. I want to be able to distinguish these things by looking at realistic durations. So in order to do that, I have to synthesize the corresponding pulse and get durations that I can actually distinguish between.
I see. So this relates to this mixed-radix architecture because, okay, so sorry, really I might be asking very simple questions, but is the idea here that because you've never had to worry about like this problem at all before of like treating a Q-core as a qubit, so you need like new pulse sequences and you need to worry about whether they're feasible and so on?
Yeah, I think, so from a practical point of view, we want to actually run them on device. And so we need to know what is that pulse sequence. And we want to kind of understand, I think it's way back here, actually, or this one maybe? No? Oh, it's very fast. Okay, remember I showed some plots of like, as a scaling dimension, the duration of say X gates, H gates, you know, these kind of simple gates kind of goes up. And so the theory told us beforehand, it's going to scale quadratically. But we didn't know what the coefficient on that was. If it was like 1 trillion, right, there's almost no practical advantage from increasing to 3 or 4. But if we actually synthesize them, we can get an actual comparison and use that to inform a compiler on which things to encode, which gates to use, et cetera.
Thank you so much.
Yep.
All right, thank you for the talk. Coming in as a theorist, I just want to get a broader overview. You've talked about pulses, but I was wondering if there is a definitive answer to which platform would implement best qubits with higher dimensions or multi-qubit gates?
Yeah, that's a good open question. So we're doing some work with experimentalists to try to figure out that question. So in the original work, 4 years ago, we compared between superconducting qubits and trapped ions, both seeming to have kind of reasonable use cases. There are some examples of like Qtrit and Q-core devices. I think, say, Berkeley has one that goes up to 4 or even more levels than that, which is superconducting. I think there's still kind of an open question there, and I think we're not sure yet. And so we're hoping that we can kind of convince experimentalists to take these sample circuits, run them, and give us kind of an idea of which of these parameters are, the sticking point, the limiting factor.
Cool, thank you.
Wonderful talk. My question was, so it seems like most of these architectures that you studied were based off superconducting, the superconducting architecture. I was wondering if you see any comparisons with like Qudit ion trap systems, and if there were any like advantages compared superconducting versus ion trap Qudit systems.
Yeah, I think so. We're currently working on doing some of the pulses for trapped ions to get a sense for how feasible it is going to be on other systems. It's kind of easy to do for superconducting qubits. I think the trapped ion Hamiltonian gets really complicated really fast, especially when the chains are long. And so it becomes kind of a harder problem to figure out the corresponding pulses. And so it's an open question, I think.
Oh, thank you.
Hello, thank you so much for your talk. I have two questions. First is, I'm curious, have you considered adapting these mixed-radix techniques to the fault tolerance setting? For example, let's say you have some Qudit code that you can use to mitigate leakage errors because the physical information carriers are Qudits, and then you want to do you still foresee any potential advantages of doing logical qubit gates encoded as operations within a Qudit error correcting code?
Short answer is I'm not sure. I think we're thinking about it, but so far it's like, it's not obvious how you can just make use of this physical kind of version and use it for something logical. Yeah, I'm not sure. I don't have a good answer for you, but it's a good question. It's an important one to answer is, does any of this matter once we get error correction?
Related to that is my other question. So I wanted to know, or just curious, any strategies for compiling emulated gates? So a lot of these is about searching for qubit logical gates, but you're within the Qudit systems or other Qudit dimensions. I believe you can have exact synthesis for any classical reversible gate for any D-array classical reversible gates where D is the Qudit dimension into 1 and 2 Qudit gates. But are there efficient ways to search for good implementations that only do what you want on the 0-1 subspace and then you don't care what it does on all other?
Yeah, so when we do the pulses, we can specify exactly that we want certain states to not be changed. So we could do, it's exactly what we found in the subspace gates. We just specified that this should not be modified. And I think maybe you were hinting at, could you just do full Qtrit gates or full Q-core gates? We could. They get really expensive really fast. And so we found that you want somewhere in between where you're doing, like thinking about these as 2 qubits and 1 Q-core actually was advantageous because we didn't need to think about manipulating the whole system or the whole kind of state at once. We're going to think about only manipulating subspaces and specifying, like you suggested, that some things don't change over the course of the pulse.
Oh, okay.
Yeah.
Thank you so much.
Okay, I guess that's all the questions. I'll be around if people have other questions they want to ask. Thank you.